So they discovered electrons. There's particles inside of the atom, and so this, of course, led to more questions. Questions like, well, if there's negative particles, there must also be positive particles in there. And how do these opposite charges fit together? We know that opposites attract. Do they just all squish together in the middle? Are atoms a jumble of even more fundamental particles? So we've seen the negative one. There's got to be a positive one, or are there a whole bunch of other ones in there? They didn't know. Are atoms solid spheres? How could they be when they have these individual particles in them? What are those little particles like? Are those solid spheres? Or do they have some sort of internal structure as well? So Thomson, the guy who was playing around with the cathode ray, he proposed what's called the plum pudding model. Now, personally, I've never had plum pudding. Anybody here had plum pudding? It's an English dessert. It doesn't sound all that appetizing to me. The closest equivalent I think that we have in terms of this analogy would be something like a blueberry muffin. So we've probably all at least seen a blueberry muffin, right? You've got the muffin part, and then it's got blueberries in it. They're kind of stuck, and they're randomly around. So that's the idea here, is that the atom is like a blueberry muffin, where the electrons are the blueberries, and the cakey muffin part is the positive charge. So that was his idea. His hypothesis. He says, I think this is what it is. Okay, so we have to take a little detour here. Radioactivity. Radioactivity is the emission of small energetic particles from the core of particular unstable nuclei. Not everything is giving off radioactivity. This was discovered at the end of the 19th century, Henri Becquerel and Marie Curie. And I just need to tell you about this a little bit because they used radioactivity to probe the structure of the atom. There are three main types, alpha particles, beta particles, and gamma rays. And what we're interested in here are the alpha particles. Alpha particles have positive charges, and of the three types of radiation, they are the most massive. Okay, a lot more about radioactivity will be covered in Chapter 20, which is in a class called Chem 1B, so we're not going to be going there. But anyway, we now know enough. Okay, so Ernest Rutherford, he had worked with Thomson, and he believed Thomson's hypothesis about the plum pudding blueberry muffin model was correct, and so he did an experiment that was designed to confirm this, because we have a hypothesis and then we test it with an experiment. So what he did is he took positively charged alpha particles and directed a beam of them at a very, very thin sheet of gold. The plum pudding model predicted that those particles would go right through the gold foil. So what happened? Well, a lot of them went through. So here's the setup. Here we have a source of alpha particles. So there's this beam of alpha particles, a little bit like, a pitching machine for baseball. Think of it as throwing baseballs here, except they're little teeny tiny alpha particles. Throwing them at this piece of gold foil. A lot of them went through. And this circular thing around here is a screen that detects the alpha particles, gives off a little pinpoint of light when it hits. So most of them went through. Some of them kind of went off course, and then a few of them bounced back. This was not expected. Approximately 1 in 20,000 bounced back. And Rutherford's comment about this was that it was about as credible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So you've got a big gun, a 15-inch shell. You're firing it at a piece of tissue paper. What do you expect? It's going to blast through the tissue paper. No, it comes back and hits you in the face. Would you be surprised? I would be shocked. You might be dead too, but... So that's, literally shot a hole in the plum pudding model. Obviously, this isn't correct. So what do we do? we come up with a different explanation. Okay, so we've got more information, we come up with a different explanation. So this was the plum pudding model. We've got this positive charged sphere, which is really nothing. And then we've got these electrons just kind of scattered about like blueberries. These particles going through, anywhere there was the muffiny part, you would expect that they would just go through. Well, they did go through, but some of them bounced back. There must be something in there that they can bounce off of. So Rutherford decided that matter must not be as uniform as it appears, and there must be large regions of empty space, because most of the particles went through. But there must be some small regions of incredibly dense matter. And so this is called the nuclear model, and this center here is called the nucleus, and that is the center of extremely dense matter. This nucleus, we now know, contains two different particles called protons and neutrons. And this yellow part here is like an electron cloud, little teeny tiny electrons just kind of scattered about in this region. So Rutherford proposed the nuclear theory of the atom. Most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. Most of the volume of the atom is empty space, and in that empty space we have tiny negatively charged electrons that are distributed. Didn't really comment on how are they distributed. That's a whole other issue. There are as many negatively charged electrons outside the nucleus as there are positively charged particles inside the nucleus. So the atom's electrically neutral. They knew from experiment that the atom does not have a charge on it. So if you have negative charges, you have to have positive charges. Those positively charged particles are called protons. So now we've got electrons and protons, and this was great. It explained lots of things, but it still wasn't quite complete. Problem is, if we look at hydrogen, a hydrogen atom has one proton, and a helium atom has two protons. We can tell that from the number of electrons from other experiments. So if the protons are the particles that have mass, we would expect that a helium atom would weigh twice as much as a hydrogen atom, because it has two massive particles to hydrogen's one massive particle. But the mass of helium is 4 times that of hydrogen. What's up? Well, Rutherford, one of his students, Chadwick, demonstrated that unaccounted for mass was due to another kind of particle called a neutron. And neutrons are neutral particles within the nucleus. So the nucleus has protons with a positive charge, neutrons with no charge, but they both have mass. So then we can explain why helium is 4 times as heavy. It does have 2 protons, but it also has 2 neutrons. So it has 4 massive particles to hydrogen's 1. Neutrons have no electrical charge. They are neutral. Protons, positive. They both start with P. Neutrons, neutral. They both start with N. Okay. The mass of a neutron is similar to that of a proton. For most purposes, we can consider it to be the same. So the hydrogen atom has 1 proton, helium atom has 2 protons and 2 neutrons, and that explains the mass. Yes?
How do neutrons and protons interact?
Yeah, that's a good question. How do protons and neutrons stay together in the nucleus? Because positive charges repel each other, right? That's a very different discussion beyond the scope of the class. Yeah. It's a good question, though. And why don't the electrons just fall into the nucleus? That's a good question as well. Structure of the atom. So now we know there's 3 main particles. They're called subatomic particles because they're smaller than the atom. The nucleus is extremely dense. It has over 99.9% of the mass of the atom, but occupies very little space. So one way to get your mind around this is to think about a cloud. Right? We've had lots of clouds lately. It's great. A cloud is composed of little tiny droplets of water, right? When clouds form down on the ground where we are, we call them fog, and we've had some of that too. When you walk through fog, is it like walking through a solid object? No. It's kind of damp, but you can pass through it very easily because most of fog is empty space. So electrons are like water droplets in a cloud. They're very small, they have negligible mass, but they're dispersed over a large volume, and so they take up a lot of space. The fog takes up a lot of space. Clouds and atoms are both mostly empty space. So, if atoms are mostly empty space, how can things appear to be solid? These bench tops appear to be pretty solid, right? You don't want to fall and hit your head on that. It's really hard. Matter appears solid because the variation in the density between that electron cloud and that little teeny tiny nucleus, the variations there are too small for our eyes to see. So if we think about scaffolding, the stuff that they put up on the outside of buildings, you know, when they do work outside. If you think about some scaffolding, scaffolding the size of a football field, that's a lot of scaffolding, and 100 stories high. If you go up close and look at it, you see that it's mostly empty space, right? You could climb through it. Some of my kids, actually I think all of my children, even my 23-year-old son, would have an awesome time climbing a scaffolding like that, right? They were like, giant jungle gym. If we looked at this scaffolding, so here's a little guy, right? So there's some scale here. If we saw this scaffolding from a long distance away, say from outer space, satellite picture, it would look solid because of all these bars, throughout. When you try to look through it, unless you're just at the right angle, it looks like it's solid, and yet it's mostly empty space. If this was an atom, the nucleus would be the size of a pea. This scaffolding, the size of a football field, 100 stories tall, would be the volume of the atom. The nucleus would be the size of a pea. And then you'd have maybe 10, 50, 100 electrons. And the electrons are even smaller than the pea, mostly empty space. So when I tap my knuckle on the bench top here, my hand doesn't pass through the bench because it's like taking one giant scaffolding and crashing it into another. They're mostly empty space, but they can't fall into each other. That make sense? That's the attempt to give you a picture of what the atom's like.